This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. And in this lecture, we're talking about Learning Objective 3.3, which looks at impulse and momentum. This is chapter 13.3 from your Beer and Johnson textbook. And this is yet another sub-branch, another tool in our study of kinetics, the interactions between forces, masses, and acceleration. Now, just like work energy, we defined work and we're able to calculate kinetic energy. In this case, we're going to start with momentum. Now, linear momentum, the symbol we'll use is an L, is a vector quantity, and it's equal to the mass of an object times its velocity. And when we think about this momentum, it's going to really set us up for some new types of problem solving that we have here. This is a vector quantity, and its units are equal to, say in US custom or in SI, kilogram meters per second. But that's also equal to a Newton second. So that's going to be very helpful to us. Or possibly, slugs, all that jazz, it would be a pound second in US customary. So that's momentum, kind of on the face of it. Mass times its velocity. Now, what happens is if we take this idea of momentum and we add to it our equations of motion, we'll get impulse. And again, you should check your textbook for the derivation of this. But the basic idea is that the impulse, also a vector quantity, is going to be equal to the integral of the force times the time it acted. Okay, now this is generally applicable, and what we'll end up with is an impulse momentum equation that says the sum of the impulse, the sum of all the forces acting on the body, times the time, sorry, this should not be ds, this is dt, times time is going to equal to the change in linear momentum. And so we're going to draw some diagrams that would look something like this, where we would be able to sketch the impulse, the force times its time, and it's going to be equal to the change in the linear momentum. So final mass times velocity minus the initial mass times velocity. I would want you to go ahead and add this to your FE reference handbook on page 80. It doesn't appear in quite this way, and in fact your textbook rearranges this equation slightly, and it says that your final mass times velocity is equal to your initial mass times velocity plus the impulse, which is also a fine way to think about it. I like this form of the equation because it looks very much like our work energy equation that we've gotten used to using. And so when we think about this, this is going to be particularly applicable when the time we're dealing with is fairly short, so that we can assume that this force is acting in a relatively constant manner. And so often what we will talk about is impulsive forces. An impulsive force is typically one that has a very large force over a very small time. And so the idea is that it's going to rapidly change the linear momentum, the mass times velocity. And so if this is true, we can assume that the integral of the force is equal to like the average force, that it's a constant, right? And then if it is a constant, then our impulse, we can say, is equal to that average force times the change in time. And so anytime we have a relatively constant force or an average force, our impulse simplifies down to the force times the time. And this is a pretty easy equation to work with. And it turns out there's a lot of cool examples that we could talk about there. So in this experiment, we have a 15-pound medicine ball, and I'm going to drop it from about waist height onto this bathroom scale. Now, if we think about impulse momentum, the momentum is going to change from it falling downward to coming to stop, to at rest. And what we should see is that the force that is applied over the time, that impulse, is equal to that change in momentum. And so if the time is very small, as will be the case here, we should see a very large increase in the force. Let's look at that video. In this case, we have just the box by itself. And so we're going to have a very rigid response. Now, I've got this set to an extremely slow playback speed. So this is slow-mo and then reduced by to additional 10%. And we'll see here that the load hits and the load goes up to, it looks at about 190 with that little freeze frame. And then it drops back down and the ball actually bounces several times. In this next recording, we have a pillow inside the box. And so the pillow is going to extend the time of impact and hopefully generate a smaller force. So more time, less force. So again, we see the load jump up as it falls. And you can see it's increasing a lot more slowly, and it peaks out at about 140 before it drops back off. And we'll also notice that it doesn't oscillate nearly as much because it basically comes to a stop in the one hit. And so when we think about this, what we've seen is that in the rigid case, it is catching the load very quickly and getting about 190 pounds of force to bring it to a stop. But in this second case with this pillow here, this cushion, it's increasing the time of that initial hit and resulting in a lower force of around 140 pounds. And so about a 50-pound decrease. Keep in mind, this is a 15-pound medicine ball that's generating that much force. Another example we could talk about is debris impact. So that video came from Texas Tech University. Texas Tech University is known for its debris impact testing because that's the way we classify tornadoes. So tornadoes are classified as, or tornado shelters, sorry, we design tornado shelters for debris impacts. Typically those 2x4s were all flying at about 200, I think it's 125 miles per hour that they hit the walls, and looking at ways that we can resist that motion. Now, when we think about resisting that motion, we see that the time of impact is very small. It's the epitome of an impulsive force. It's just punching that wall super hard, which means that we're getting a very large force to take a mass of a couple of pounds for a 2x4 times a velocity of 125 miles per hour and have it go all the way to zero, right, to stop it. And in some cases, we saw that it didn't go to zero, just zipped right through the wall. So we have those impulsive forces going on. Now, one way that we can do this is we can just make a really stout wall so that it can handle that very high force. The other way that we can do this is by increasing the duration of the impact. So if we increase the duration of the impact, we get less force needed to result in that same change in momentum. And so one way that we can do this is with Kevlar. So Kevlar stops bullets by basically stretching. So there's two ways we can think about it. We can think about it in terms of work energy, where that force is that Kevlar is deforming and dissipating energy, right? So we're losing energy to slow down the bullet or the projectile. In the case of impulse momentum, remember these are the same ideas, they're just dressed differently. It's a different arrangement of the equation of motion equation. What we're seeing here is that we're increasing the time to have less force required. And so I've heard of an example of a Kevlar storm shelter, which stretches. So you fire that 2x4 into it and it stretches. Now it requires some stretch. The guy that I got the video from, I used to be friends with the guy that ran the cannon, and he set up a test in which he noticed that as they were building their Kevlar storm shelter, they had a 2x4 size gap with some Kevlar stretched over the top of it. No one asked his opinion, but he was able to line it up and punch that hole. And because the Kevlar didn't have enough sheeting to give, it actually ended up just ripping right through the middle of the Kevlar. And so kind of a funny thing that we have to think through how it's going to stretch, how it's going to increase the time. Our cell phone cases are another example of a technology intended to increase the time of the impact so that the impulsive force can be less by increasing the change in time. This also brings us to non-impulsive forces. Non-impulsive forces typically are going to have a relatively small force over a small time. Which means that the impulse is approximately zero. So remember, when we're thinking about using a engineering or math model, we want to make sure our mental model is engaged and that we're making good choices. And so an example here that we might have is that when we think of that impulse momentum, if we're looking at like let's say a baseball that's getting hit by a bat, we know that the bat is exerting an impulsive force. There's very little time and a large amount of force because we see the ball change directions, right? But at the same time, weight is also acting on it, right? But a 4-ounce ball compared to, 100 pounds of force from a bat, we'll actually do a problem and we'll see what that math might work out to. Over a very tiny amount of time, it's really not going to change the trajectory of the ball all that much, that weight during the time of the impact. And so when we think of these non-impulsive forces, we're typically going to use them to simplify our equations so that we can set up an impulse momentum equation that's easier to solve. So we've talked about Kevlar, we've talked about the storm shelters. Another example of this impact impulse would have to do with, so I have a colleague who had a boss who would actually measure the density of soils that were compacted using a golf ball. He'd bounce the golf ball, and he had a good sense for how much rebound was needed for his materials to be properly compacted. And it turned out that the more time, because of the deformation of the material, the less helpful, or the less that the ball would bounce back up. And so he knew that he needed to do more compaction through there. So that's another example of impulse momentum. We'll work some problems together in class, and I look forward to seeing you then. Thanks. Bye.